Hi, I'm Victor. Welcome to the uORover System Acceptance Review. We are a first-year robotics team from the University of Ottawa. We first got interested in a challenge when we went to see the competition last year in Utah. And over the past 8 months, we've been working hard on designing and manufacturing the various components of the rover. And I'm proud to say we have moved on to testing to ensure rover readiness for May. In this review, we'll be going over the hardware and software capabilities of a rover, as well as how we plan to achieve the science mission.
Hello, my name is Hiba and I'm the science team lead for uORover. Part of the science mission is to determine whether there is an extant or no life in the soil or rock samples we're analyzing. We will have 4 quantitative tests that will detect the presence of nitrogen, potassium and sulfate in the soil, all along with the pH test.
Hi, my name is Michelle and I am a member of the science team. We will collect the soil via a vacuum. These quantitative tests will consist of mixing the collected soil with a reactive powder and water in pre-filled test tubes and will change colors according to the individual test. The darker the pigment, the more of that ion is present in the soil. As you can see, these experiments depend on visual observation and a color comparison chart. We will observe the color change remotely through the cameras that will be fixed on our rover. The data collected will then be analyzed with our color comparison chart. During our preliminary stages, we tested known concentrations of nitrogen, potassium, and sulfate to correlate the color with the concentration of these ions. This means that when distinguishing the color, we can estimate the concentration of these ions in the sample as well.
The cameras will also be used to characterize the rocks in order to identify and determine if there are traces of life present on the rocks. In addition to that, pH determines if the substrate is an optimal environment for organisms to live in. Most plants require soil to have a pH of 5.5 to 7. This is an indicative range where life forms could survive in this pH environment.
For the autonomous traversal mission, the rover will use a mounted LiDAR system to perform simultaneous localization and mapping of the environment. We've chosen to use LiDAR because it is more accurate than camera-based sensing and it is also much less computationally expensive. As the rover traverses the environment, the LiDAR will create a 3-dimensional map that will show large obstacles in the field. If the rover encounters an obstacle, it modifies its trajectory to avoid it while remaining on path to the checkpoint. Once the rover makes it to the GPS checkpoint, it will switch into vision mode. The rover will use Python's OpenCV library to locate the symbol. The onboard computer will use computer vision techniques to isolate the symbol from the surrounding image and then apply a bounding box to it. The rover will then move in the direction to maximize the area of the bounding box. Finally, the rover will report to the base station once it has reached the symbol.
Our rover takes advantage of 2 methods for communication. The first uses the common 2.4 GHz band for testing locally within our work bay. Our second uses the 900 MHz band for a more reliable, long-range connection to our base station. At competition, we will be planning to use an omnidirectional antenna on our rover and a directional antenna on our base station, both being paired with a high-throughput transceiver.
Hi, my name is Hridyansh. Rover suspension is a double wishbone design. We chose this configuration due to its compact design as well as its ability to maintain its camber angle during traversal. Shock absorbers are mounted to each wheel to dampen against any bumpy rides the rover experiences throughout the missions, and these shocks can also be replaced with fixed supports during missions over flat terrain. Each wheel is custom designed and consists of 2 tires for fine handling over rough terrain and is direct driven through a 8-to-1 gear reduction that generates enough torque to translate over 30 degrees inclined slopes. By having motors inside each wheel, we lower the rover's center mass, reducing the possibility of tipping. Furthermore, having 4 independently controlled wheels allows the rover to turn in place, which will prove advantageous during missions such as the extreme retrieval as well as the autonomous traversal. The robotic arm used on the rover is called the AR3, an open source 6 degree of freedom arm that has been chosen for this project to reduce development time. While all of the core structural components for the arm were already laid out, major mechanical changes were made to allow the AR3 to handle the 5 kg load requirement. Each joint is actuated using geared stepper motors and optical encoders, enabling the arm to perform with a 700mm sphere. The modular design of the arm allows for it to be adapted for each mission as well as for easy detachment. Our next step is to test the arm in the field and observe how many structural components behave under vibration, fluctuating temperatures, and varying load requirements.
In the final months leading up to URC, we plan on stress testing the full system and providing a full array of training to our operators. We have learned so much in the past 8 months, and I'm really optimistic about our performance in 2020.